The story of Andromeda begins with a breathtaking view, a vast spiral galaxy shining quietly in the night sky, far beyond the reach of our own Milky Way. For thousands of years, people gazed up at the faint, misty patch in the constellation Andromeda, not knowing what it truly was. Ancient astronomers recorded it as a mysterious cloud, barely visible to the naked eye on the darkest nights. In the 10th century, the Persian astronomer al-Sufi described the Andromeda Galaxy as a little cloud in the night sky, noting its faint, misty appearance. Centuries later, with the invention of the telescope, astronomers such as Simon Marius and Charles Messier were able to observe Andromeda in much greater detail. They carefully sketched its hazy form and catalogued it as Messier 31, recognizing it as a distinct object in the heavens. These early observations marked the beginning of our scientific understanding of Andromeda, transforming it from a mysterious patch of light into a subject of careful study and curiosity. For centuries, astronomers debated what Andromeda truly was. Some believed it was a small cloud of gas within our own galaxy. Others wondered if it might be an entire island universe, a galaxy in its own right, unimaginably far away. The answer came in the 1920s, when Edwin Hubble used a powerful telescope to spot special stars, Cepheid variables, inside Andromeda. By measuring their brightness, he proved that Andromeda was far outside the Milky Way, a galaxy of its own, millions of light-years away. Today, we know that Andromeda is our nearest large galactic neighbor, a majestic spiral galaxy teeming with stars, dust, and gas. It is the largest galaxy in our local group, even bigger than the Milky Way. Through modern telescopes, Andromeda's spiral arms and bright core are revealed in stunning detail. Its disk stretches more than 200,000 light-years from end to end, containing roughly 1 trillion stars, more than twice the number in the Milky Way. Yet even with so many suns, the space between them is immense. If Andromeda and the Milky Way ever pass through each other, simulations show that individual stars will almost never collide. The distances are simply too great. Andromeda's visible disk is surrounded by a faint halo of stars, dust, and gas, making the galaxy even larger than it first appears. Light from its near side takes about 2.5 million years to reach us, while light from the far side takes tens of thousands of years longer. In a very real sense, we see different parts of Andromeda at different times. Its light is a message from the distant past, carrying secrets of how galaxies form and evolve. This shimmering spiral has inspired wonder for generations. From ancient skywatchers to modern astronomers, Andromeda remains a symbol of the vastness and beauty of the universe, and a reminder that our own Milky Way is just one galaxy among billions. Slow, beautiful pan across Andromeda's spiral arms, highlighting dust lanes and the glowing core. Gentle camera drift evokes a sense of wonder. In space documentaries, music interludes like this one help set the mood and give us a moment to reflect on the vastness of the universe. The gentle music and sweeping views of Andromeda invite us to pause, breathe, and appreciate the beauty and scale of the cosmos. It transitioned to a new angle of Andromeda's spiral, with a gentle camera move across the faint outer halo. The scene remains calm and contemplative, letting the music carry the moment. A changing understanding. At the start of the 20th century, scientists were divided. Some, like Harlow Shapley, believed the Milky Way was the entire universe, and that all spiral nebulae, including Andromeda, were just clouds of gas within it. Others, such as Heber Curtis, thought these nebulae might be island universes, huge collections of stars far beyond our galaxy. This disagreement led to heated debates in scientific journals and meetings. The most famous of these arguments was the Great Debate of 1920. In a packed hall, Shapley and Curtis presented their ideas. Shapley argued that the Milky Way was so large that everything, including Andromeda, must be inside it. Curtis disagreed, saying that Andromeda was a separate galaxy, far outside the Milky Way. The debate ended without a clear winner, and the mystery continued. Everything changed in 1924, when Edwin Hubble used a powerful new telescope at Mount Wilson Observatory. He discovered special stars in Andromeda called Cepheid variables. By measuring how these stars brightened and dimmed, Hubble could calculate their distance. He found that Andromeda was far outside the Milky Way, over 2 million light-years away. This meant that Andromeda was not a cloud in our galaxy, but a galaxy of its own, filled with billions of stars. Hubble's discovery changed everything. Suddenly, the universe was much bigger than anyone had imagined. Andromeda became our nearest large galactic neighbor, and scientists realized there were countless other galaxies beyond our own. This was a turning point in astronomy. It showed how science moves forward, by asking questions, debating ideas, and using new tools to find answers. Today, modern telescopes and space missions have revealed even more about Andromeda. High-resolution images from the Hubble Space Telescope show hundreds of millions of stars in just one part of the galaxy. We now know that Andromeda is a barred spiral with long arms of stars, dust, and gas winding out from its core. Infrared and ultraviolet images highlight where new stars are born and where old stars gather. Our understanding keeps growing, thanks to the work of many scientists over time. The rise of structure from cosmic dawn to Andromeda. As the universe expanded, it cooled. After about 380,000 years, temperatures dropped enough for electrons and protons to combine and form the first atoms, mostly hydrogen with a little helium. This era is called recombination. For the first time, light could travel freely through space, creating a faint glow that we still detect today as the cosmic microwave background. For hundreds of millions of years, the universe was dark and nearly featureless. This period is known as the Cosmic Dark Ages. There were no stars or galaxies, just vast clouds of cold hydrogen and helium drifting through space. But gravity was at work, slowly pulling matter into denser regions. Over time, these denser pockets of gas became the seeds of the first stars. When enough material gathered, gravity squeezed the gas until it ignited nuclear fusion. The first stars were born, brilliant, massive, and short-lived. Their light ended the cosmic dark ages and began to shape the universe. These first stars created and scattered new elements, carbon, oxygen, and heavier atoms, when they exploded as supernovae. Their energy and material spread out, enriching the surrounding gas and making it possible for new generations of stars to form. As the universe continued to evolve, gravity pulled gas and dark matter into larger and larger structures. Small clumps of stars and gas merged together, forming the first tiny galaxies. These building blocks collided and combined, growing into bigger galaxies over billions of years. Andromeda, like our own Milky Way, was built from these smaller pieces. Over time, it grew by drawing in gas and merging with other galaxies. Each collision stirred up the gas, triggered new waves of star birth, and left behind chemical fingerprints in the stars we see today. Today, Andromeda sits at the heart of a web of dark matter and gas, surrounded by smaller galaxies. Its vast disk and ancient star clusters are fossils from this long history. By studying Andromeda's stars and their chemical makeup, astronomers can trace the galaxy's ancestry all the way back to the cosmic dawn. The story of Andromeda is the story of the universe itself. How simple clouds of gas, shaped by gravity and time, became the magnificent spiral galaxy we see today. From the first atoms to the birth of stars and galaxies, Andromeda's history connects us to the very origins of the cosmos. a galaxy built through fire and fusion. Over time, these stars gathered into small galaxies. Andromeda began as one of these tiny galaxies, growing larger as it merged with others. Each collision was like a cosmic fireworks show. Galaxies smashing together, gas clouds mixing, and new waves of starbirth lighting up the darkness. These violent events left behind clues in Andromeda's stars. Some stars have much more oxygen than iron, while others have a more balanced mix. This tells astronomers that Andromeda's stars formed in different ways and at different times. Astronomers study the light from Andromeda's stars to learn about these ancient events. By splitting starlight into a rainbow of colors, they can see which elements are present. This is called spectroscopy. It's like reading a barcode that tells the story of each star's birth. The different amounts of oxygen and iron show that Andromeda did not form all at once. Instead, it grew through many dramatic episodes, each one leaving a chemical fingerprint in the stars. One of the biggest events in Andromeda's past was a giant collision with another galaxy, sometimes called M32P. This galaxy may have had tens of billions of stars. When it crashed into Andromeda, much of its material was torn away. The remains became a small, dense galaxy called M32, which still orbits Andromeda today. The collision also triggered a huge burst of star formation. About 1 in every 5 stars in Andromeda was born during this time. Andromeda's disk is filled with many types of stars. Some are young and hot, shining blue and white. Others are old and cool, glowing red. There are also clusters of stars, groups that form together from the same cloud. By studying these different stars, astronomers can piece together the timeline of Andromeda's growth. Each type of star adds a new chapter to the galaxy's story. Today, Andromeda is a survivor of many cosmic battles. Its structure, spiral arms, bright core, and faint halo, was shaped by fire and fusion. The heavy elements in its stars are the ashes of ancient explosions. By looking at Andromeda, we see not just a galaxy, but a living record of the universe's history. Every star, every cloud, and every element tells a part of the story of how galaxies like ours came to be. Star formation today. When we look at Andromeda and the Milky Way, it's tempting to think of them as cosmic siblings. But their star-forming activity is very different. The Milky Way creates about 6 or 7 new stars every year, while Andromeda forms only about 1 or 2. This difference is striking, and it tells us a lot about the life cycles of galaxies. Astronomers measure star formation by looking for the telltale glow of hydrogen gas in star-forming regions, and by counting the number of young, massive stars. In Andromeda, these glowing clouds, called H2 regions, are much less common than in the Milky Way. This means that Andromeda's spiral arms are quieter, with fewer bright nurseries where new stars are born. The main reason for this slowdown is that Andromeda's supply of cold molecular gas, the raw material for making stars, has been used up or blown away by past bursts of star formation. Without enough fresh gas, the galaxy can't build many new stars. Most of the stars that do form now are small, cool red dwarfs, rather than the hot, massive stars that light up the galaxy. By contrast, the Milky Way still has plenty of gas and dust, so it continues to build new stars and stellar nurseries. This is why our galaxy's spiral arms are filled with bright, young stars and glowing clouds. In Andromeda, the older stars dominate, giving the galaxy a more settled, mature appearance. Over time, both galaxies will use up their remaining gas. Star formation will slow to a trickle, and the galaxies will be left with long-lived red dwarfs. For Andromeda, this means its days of making new stars are mostly behind it. But by studying these changes, astronomers learn how galaxies grow old and how the universe itself evolves. How stars are born and die. To understand the story of Andromeda, we need to know how stars live their lives. Every star begins inside a giant cold cloud of gas and dust, called a nebula. These clouds are like cosmic nurseries, floating in the arms of galaxies. In Andromeda, you can see bright patches where new stars are being born right now. Inside these clouds, gravity slowly pulls the gas together. As the gas clumps up, it forms a dense ball called a protostar. The protostar gets hotter and hotter as more material falls in. If you could look inside a nebula, you would see many of these baby stars glowing softly, hidden by dust. When the center of the protostar gets hot enough, nuclear fusion begins. This is when hydrogen atoms join together to make helium, releasing huge amounts of energy. The star lights up and joins the main sequence, the longest stage of its life. Most of the stars you see in the night sky, including our Sun, are main sequence stars. In Andromeda, billions of these stars shine in the spiral arms. Stars come in many sizes and colors. Small stars, called red dwarfs, burn their fuel slowly and can live for tens of billions of years. Bigger stars, like our Sun, shine for about 10 billion years. The most massive stars are blue and very bright, but they use up their fuel quickly and live only a few million years. As a star runs out of hydrogen, it changes. A star like the Sun swells up into a red giant, growing much larger and cooler on the outside. In this stage, the star can swallow nearby planets and shed its outer layers into space, creating beautiful clouds called planetary nebulae. The core that remains becomes a white dwarf, a small, hot and dense star about the size of Earth. White dwarfs slowly cool and fade over billions of years. In Andromeda, many old stars have already become white dwarfs, quietly shining in the darkness. Massive stars end their lives in a much more dramatic way. When they run out of fuel, their cores collapse and the outer layers explode in a supernova. A supernova is one of the brightest events in the universe, briefly outshining an entire galaxy. These explosions scatter heavy elements like oxygen, carbon and iron into space, making the building blocks for new stars and planets. After a supernova, the core left behind can become a neutron star, or, if it is massive enough, a black hole. Neutron stars are incredibly dense, packing more mass than the Sun into a ball just a few kilometers wide. Some neutron stars spin rapidly and send out beams of light, called pulsars. Black holes have gravity so strong that not even light can escape. All these stages, starbirth, shining life, and dramatic death, happen again and again in galaxies like Andromeda. The heavy elements made in dying stars mix with gas clouds, helping to form new stars, planets, and even life. By watching Andromeda's star-forming regions and the remains of old stars, astronomers learn how the universe recycles itself, one star at a time. From clouds to stars, the interstellar medium. When we look at galaxies like Andromeda, we see bright stars and swirling arms, but most of the space between those stars is not empty. Instead, it is filled with the interstellar medium, or ISM, a vast, invisible ocean of gas, dust, and energy. The ISM is the birthplace of all stars and planets. It is made up of different types of gas. Some is hot and thin, some is cold and dense, and some is in between. The warm neutral medium is like a gentle fog of hydrogen atoms, spread thinly across the galaxy. The warm ionized medium glows with energy from young hot stars, while the cold neutral medium forms thick clouds where atoms can stick together. Deep inside these cold clouds, hydrogen molecules form and temperatures drop to just a few degrees above absolute zero. Dust grains float within these clouds, acting like tiny shields that block starlight and help cool the gas. These grains are made of silicates, carbon and ices, and they play a crucial role in the chemistry of space. Without dust, molecules like water and ammonia could not form, and planets like Earth would never exist. The ISM is not still. It is constantly stirred by energy from stars, supernova explosions, and even the movement of the galaxy itself. This energy creates turbulence, mixing the gas and dust and shaping the clouds into filaments, knots, and bubbles. Gravity is the force that brings order to this chaos. When a region of a molecular cloud becomes dense enough, gravity pulls the gas and dust inward, causing the cloud to collapse. But this collapse is not smooth. Turbulence tears the cloud into filaments, and along these filaments, matter funnels into dense knots. These knots become protostars, the seeds of new suns. Magnetic fields thread through the gas, sometimes slowing collapse, sometimes guiding it. Shock waves from supernovae or the spiral arms of the galaxy can also compress clouds, triggering new waves of star formation. Astronomers study the interstellar medium using many tools. Radio telescopes can detect cold hydrogen gas, while infrared telescopes reveal warm dust hidden from visible light. By mapping the ISM in Andromeda, scientists can see where new stars are likely to form and how past generations of stars have shaped the galaxy. They use computer simulations to model how gas moves and collapses, and they compare these models to real images from space telescopes. These studies show that the ISM is always changing, with gas turning into stars, stars enriching the gas with new elements, and the cycle beginning again. The interstellar medium is the engine of galactic evolution. Without it, there would be no new stars, no planets, and no life. By understanding the ISM in Andromeda, we learn not only how galaxies grow and change, but also how our own Sun and Earth came to be. Every star, every planet, and every living thing owes its existence to the quiet, invisible clouds drifting between the stars. Star clusters and ancient relics. When we look at the Andromeda Galaxy, we see more than just a swirl of stars. Hidden within its spiral arms and outer halo are thousands of star clusters, groups of stars that form together and travel through space as a family. These clusters are like living fossils, helping astronomers unlock the story of how Andromeda grew and changed over billions of years. There are two main types of star clusters in Andromeda: open clusters and globular clusters. Open clusters are made up of a few hundred to a few thousand young stars. They are found mostly in the galaxy's spiral arms, where new stars are still being born. These clusters are loose and spread out, and over time their stars drift apart. Open clusters shine with a blue-white light, showing us where Andromeda's star formation is happening right now. Globular clusters are very different. They are tightly packed balls of ancient stars, sometimes hundreds of thousands or even millions of stars squeezed into a small space. These clusters are much older than open clusters, with ages over 10 billion years. Globular clusters orbit Andromeda in a huge halo far above and below the galaxy's main disk. Their stars are dimmer and redder, showing their great age. To help us see the difference, astronomers use simple graphics and color images. Open clusters look like scattered jewels, while globular clusters appear as bright, round balls. In Andromeda, there are about 500 globular clusters, more than 3 times as many as in our Milky Way. Each one is a time capsule from the early universe, holding clues about how the galaxy formed and changed. But how do astronomers find and study these clusters? They use powerful telescopes on Earth and in space to take detailed pictures of Andromeda. By looking at the color and brightness of each cluster, scientists can tell how old it is and what it's made of. Sometimes they use special filters to pick out clusters hidden by dust or far from the galaxy's center. Computers help sort through thousands of images to spot new clusters and measure their properties. Studying star clusters in Andromeda helps us understand the galaxy's past. Open clusters show us where new stars are forming today, while globular clusters reveal the galaxy's ancient history. By mapping where these clusters are found, astronomers can trace the paths of past galaxy mergers and see how Andromeda grew over time. Each cluster, whether young or old, is a piece of the puzzle that tells the story of our cosmic neighbor. In the end, star clusters are more than just beautiful sights in the sky. They are living records of how galaxies like Andromeda are built, change, and survive across cosmic time. Variable stars are stars whose brightness changes over time. Some pulse regularly, growing brighter and dimmer in a steady rhythm. Others vary in more complex ways. Astronomers study these changes by carefully measuring the light from each star, creating what's called a light curve, a simple graph that shows how the star's brightness rises and falls. In Andromeda's vast halo, astronomers have discovered hundreds of RR Lyrae stars, ancient pulsating stars that act as cosmic timekeepers. These stars are especially valuable because their regular pulses make them easy to spot, even in distant galaxies. By tracking their light curves, scientists can determine their age, distance, and chemical makeup. In one Hubble Space Telescope study, more than 600 RR Lyrae stars were found in a small patch at the edge of Andromeda. When astronomers analyzed their light, they noticed something remarkable. The stars fell into two groups, each with a different chemical fingerprint. This tells us that some of these stars were born in Andromeda, while others came from a smaller galaxy that was later torn apart and absorbed. By studying variable stars like RR Lyrae, astronomers can piece together Andromeda's history. These stars act as cosmic archaeologists, revealing when and where different groups of stars formed. Their chemical signatures and ages help scientists map out ancient mergers, starbursts, and the growth of the galaxy's halo. Observing these faint, flickering stars is not easy. Astronomers use powerful telescopes on Earth and in space, taking repeated images over many nights. By comparing these images, they can spot stars that change in brightness and measure their patterns. This careful work allows us to look back in time and understand how Andromeda grew and changed over billions of years. In this way, variable stars help unlock the secrets of Andromeda's past. Each flicker of light is a clue, showing us how galaxies grow, merge, and evolve. By reading the stories written in their changing brightness, we learn not just about Andromeda, but about the history of the universe itself. Cosmic clocks, Cepheids, and RR Lyrae are special types of stars that help astronomers measure the universe. These stars do not shine with a steady light. Instead, they get brighter and dimmer in a regular pattern, almost like a heartbeat. By watching how their brightness changes over time, scientists can learn important things about space. Cepheid variable stars are especially useful. The time it takes for a Cepheid to go from bright to dim and back again tells us exactly how bright it really is. If we know how bright a star should be and we see how faint it looks from Earth, we can figure out how far away it is. This is like knowing how loud a bell is and judging its distance by how soft it sounds. Over 100 years ago, astronomer Edwin Hubble used a Cepheid star in the Andromeda Galaxy to make a huge discovery. He measured its light curve, the pattern of its brightness, and realized that Andromeda was far outside our own Milky Way. This changed our view of the universe forever, showing that there are many galaxies beyond our own. Today, astronomers still use Cepheid stars to measure distances to faraway galaxies. They use powerful telescopes to watch these stars pulse and record their light curves. By comparing the true brightness to what we see, they can calculate how far away a galaxy is, even millions of light years from Earth. RR Lyrae stars are another kind of cosmic clock. They are older and fainter than Cepheids, but they also pulse in a steady rhythm. RR Lyrae stars are found in ancient parts of galaxies, like the halos around Andromeda. By studying them, astronomers can learn about the oldest stars and the early history of a galaxy. In Andromeda, space telescopes like Hubble have found hundreds of RR Lyrae stars. These stars show that Andromeda's halo is made up of stars from different times and places. Some RR Lyrae stars formed in Andromeda itself, while others came from smaller galaxies that were pulled in and mixed together. By counting Cepheid and RR Lyrae stars, astronomers can build a timeline of how Andromeda grew. Each star is like a marker, showing when and where new stars were added to the galaxy. This helps scientists map out Andromeda's history, including its mergers with other galaxies and the growth of its spiral arms and halo. Thanks to these cosmic clocks, we know that Andromeda is about 2.5 million light-years away from us. Variable stars have helped unlock the true scale of the universe, showing that our galaxy is just one of many in a vast cosmic sea. By studying their steady rhythms, astronomers continue to explore the mysteries of space and time. A zoo of variable stars. Andromeda is home to a dazzling variety of variable stars, stars whose brightness changes over time. These cosmic beacons come in many forms, each with its own story to tell. Some, like Cepheids and RR Lyrae, pulse in a steady rhythm, helping astronomers measure distances across the universe. But Andromeda's collection goes far beyond these famous examples. Mira variables are giant red stars nearing the ends of their lives. They swell and shrink over hundreds of days, growing brighter and dimmer as their outer layers expand and contract. These stars shed huge amounts of material into space, enriching Andromeda's spiral arms with carbon and other elements. Long-period variables like Miras help astronomers trace the history of star formation in the galaxy, revealing where new generations of stars once emerged. Eclipsing binaries are another fascinating type. In these systems, two stars orbit each other, and from our viewpoint, one star regularly passes in front of the other, causing the system's brightness to dip. By carefully measuring these dips, astronomers can determine the star's sizes, masses, and orbits with remarkable precision. Observing eclipsing binaries in Andromeda helps scientists test their models of how stars work, and even refine our measurements of the galaxy's distance. Cataclysmic variables are some of the most dramatic. These are binary systems where a white dwarf pulls material from a companion star. When enough matter builds up, it can trigger a sudden explosion called a nova, making the system flare up in brightness. Novae in Andromeda are less powerful than supernovae but still light up the galaxy for days or weeks. By cataloguing all these variable stars, astronomers piece together the life cycles of stars, the chemistry of galaxies, and the history of cosmic change. Powerful telescopes and careful monitoring allow scientists to spot these flickers of light, turning Andromeda into a living laboratory for stellar evolution. Stellar archaeology is like detective work for astronomers. By studying the light from stars in Andromeda, scientists can uncover secrets about how the galaxy formed and changed over billions of years. Every star is a time capsule, holding clues about the gas and dust that made it. To do this, astronomers use powerful telescopes and special instruments called spectrographs. A spectrograph splits the light from a star into a rainbow of colors, called a spectrum. Each chemical element leaves a unique pattern of lines in the spectrum, like a barcode. By reading these patterns, scientists can tell what elements are inside a star, like hydrogen, helium, oxygen, and iron. This helps them figure out when and where the star was born, and what kind of events shaped the galaxy. In Andromeda's disk, astronomers have found two main groups of stars. One group has much more oxygen compared to iron, which means it formed quickly from gas enriched by massive stars that exploded as supernovae. The other group has a more balanced mix of oxygen and iron, showing it formed over a longer time as different types of supernovae added new elements. These chemical fingerprints reveal that Andromeda's history was shaped by bursts of star formation and by mergers with other galaxies. When galaxies collide, Their gas mixes and triggers new waves of starbirth, leaving behind stars with different chemical signatures. Astronomers also study stars in Andromeda's halo, the faint outer region of the galaxy. Some of these stars are extremely metal-poor, meaning they have very few heavy elements. These ancient stars are like fossils from the early universe, showing what the galaxy was like long ago. Other stars in the halo have more metals, matching the chemical patterns of stars from smaller galaxies that Andromeda swallowed over time. By mapping where these stars are and what they're made of, scientists can piece together the story of Andromeda's many mergers. Even small details matter. Scientists measure the ratios of different isotopes, slightly different versions of the same element, like carbon-12 and carbon-13, or oxygen-16 and oxygen-18. These ratios tell us how quickly stars formed in different parts of the galaxy and what kinds of stars lived there. By putting all these clues together, astronomers can create a timeline of Andromeda's past. They can see when the galaxy had bursts of star formation, when it merged with other galaxies, and how its stars and gas changed over time. Stellar archaeology turns the Andromeda Galaxy from a simple picture into a living story. By studying the chemistry of its stars, we learn not just about Andromeda, but about how galaxies grow, change, and create the elements that make planets and life possible. The dark heart of Andromeda is one of the galaxy's greatest mysteries. At its very center lies a supermassive black hole, a region of space where gravity is so strong that nothing, not even light, can escape. This black hole is hidden within a swirling disk of blue stars and surrounded by an older ring of red stars. It contains about 140 million times the mass of our Sun, making it one of the largest known in our galactic neighborhood. But what exactly is a supermassive black hole? Unlike the black holes that form when massive stars die, these giants are found at the centers of most large galaxies. They grow by pulling in gas, dust, and even stars, becoming millions or billions of times more massive than our Sun. Their gravity shapes the motion of stars and gas around them, creating a bright, energetic region called the galactic nucleus. Astronomers discovered Andromeda's black hole by observing the rapid movement of stars near the galaxy's center. Using powerful telescopes, they measured how these stars orbit an invisible object. The only explanation for their high speeds is the presence of an extremely massive, compact object, a black hole. To study black holes, scientists use many tools. They observe X-rays and radio waves coming from the center, watch how matter spirals in, and create computer models to simulate what happens near the event horizon, the point of no return. Sometimes they even catch glimpses of flares or bursts of energy as material falls into the black hole. Even with all these discoveries, many mysteries remain. We still do not know exactly how supermassive black holes form or why they grow so large. Some theories suggest they began as smaller black holes in the early universe and grew by merging and feeding on gas. Others propose they formed directly from giant clouds of collapsing gas. By studying Andromeda's core, astronomers hope to unlock the secrets of these cosmic giants and learn more about the history of galaxies. The dark heart of Andromeda reminds us that even the brightest galaxies are shaped by invisible forces. As technology improves, astronomers will continue to peer into the core of Andromeda, searching for answers to questions that challenge our understanding of the universe. Rare stars and explosive events. Not all of Andromeda's stars are ordinary. Among its billions of suns are rare and powerful objects that help us understand the universe. Some of the most fascinating are called magnetars. Magnetars are the leftover cores of massive stars that exploded long ago. They are a special kind of neutron star with magnetic fields so strong they could erase a credit card from thousands of miles away. These fields are 1,000 times stronger than those of normal neutron stars. Magnetars sometimes release sudden bursts of X-rays and gamma rays. These flares can be so bright that for a moment, they outshine every other star in their galaxy. On Earth, scientists have even seen these flares affect our planet's upper atmosphere, even though the magnetars are thousands of light-years away. Finding magnetars in Andromeda is difficult because their flares are rare and fade quickly, but astronomers keep watching for them with special telescopes. Another rare type of star in Andromeda is the luminous blue variable, or LBV. These are giant hot stars that can suddenly become much brighter. LBVs lose huge amounts of material in powerful eruptions, blowing off their outer layers into space. These eruptions can make the star shine millions of times brighter than the Sun for a short time. Only a few LBVs are known in Andromeda, but they are important because they may explode as supernovae in the future. Andromeda also contains Wolf-Rayet stars. These are the hot, stripped cores of massive stars that have lost their outer layers. Wolf-Rayet stars blow strong winds into space, creating beautiful shells of gas and dust. They are very bright and short-lived, and their powerful winds help shape the galaxy's star-forming regions. By studying Wolf-Rayet stars, astronomers learn how massive stars live and die. The most dramatic events in Andromeda are supernova explosions. When a massive star runs out of fuel, its core collapses and the star explodes, sending heavy elements like oxygen, carbon, and iron into space. These explosions are so bright they can outshine an entire galaxy for weeks. Supernovae are important because they create the elements needed for planets and life. In Andromeda, astronomers have seen many supernovae over the years, but only one, called SN 1885A, was bright enough to see without a telescope. The remains of these explosions, called supernova remnants, can still be seen in Andromeda's disk. These glowing clouds of gas and dust expand over thousands of years, lighting up in X-rays and radio waves. Each remnant is a clue to the galaxy's past, showing where stars once lived and died. By studying these remnants, scientists learn how galaxies recycle material and create new generations of stars. All these rare stars and explosive events make Andromeda a fascinating place to study. They show us how stars are born, live, and die, and how galaxies change over time. By watching Andromeda's rarest stars and brightest explosions, astronomers unlock the secrets of the universe and our own cosmic history. The physics of magnetars and high-energy phenomena. This incredible magnetic power twists and strains the magnetar's solid crust. When the crust suddenly cracks, it releases a burst of energy, an explosion of X-rays and gamma rays that can outshine entire galaxies for a brief moment. In just a fraction of a second, a magnetar flare can release as much energy as our Sun emits in 100,000 years. These flares are so powerful that, if one happened close to Earth, it could disrupt our planet's atmosphere. Magnetars are rare and unpredictable. Astronomers must constantly monitor the sky to catch one in action, especially in distant galaxies like Andromeda. When a magnetar erupts, it gives scientists a unique chance to study matter under conditions that can't be recreated on Earth. By observing these flares, researchers hope to learn more about the behavior of matter, energy, and magnetic fields at their most extreme. But magnetars are not the only high-energy wonders in Andromeda. The galaxy is also home to X-ray binaries, systems where a neutron star or black hole pulls in gas from a companion star. As the gas spirals in, it heats up to millions of degrees and emits powerful X-rays. These X-ray binaries flicker and flare, revealing the presence of invisible objects like black holes and neutron stars. Sometimes, even more dramatic events occur. Gamma-ray bursts are the brightest explosions in the universe. They can happen when two neutron stars collide, or when a massive star collapses into a black hole. Although no confirmed gamma-ray burst has been traced to Andromeda yet, astronomers keep watch with satellites like NASA's Swift, hoping to catch one of these cosmic fireworks in action. By studying magnetars, X-ray binaries, and gamma-ray bursts in Andromeda, astronomers are pushing the boundaries of physics. These high-energy events help us understand how massive stars live and die, how matter behaves in the most extreme environments, and how the universe's most powerful explosions shape galaxies. Each discovery brings us closer to unlocking the secrets of the cosmos. Building blocks of life. The chemical story. All the atoms in your body, like carbon, oxygen, and iron, were made inside stars. When stars run out of fuel, some explode as supernovae, blasting these elements into space. Over millions of years, this material mixes with clouds of gas and dust, creating new stars and planets. This is how the universe recycles itself, turning stardust into everything we see, including us. In Andromeda, astronomers have found two main types of stars. Some are rich in oxygen, which means they formed quickly from gas enriched by massive stars. Others have more iron, showing they formed later, after special supernovae called Type Ia added iron to the galaxy. These chemical clues help scientists piece together Andromeda's history, when it had bursts of star formation and when it merged with other galaxies. To study these elements, astronomers use telescopes that split starlight into a rainbow of colors, called a spectrum. Each element leaves a unique fingerprint in the light. By looking at these fingerprints, scientists can measure how much of each element is in a star. This helps them understand how galaxies like Andromeda grow and change over time. The chemical story of Andromeda is also the story of planets and life. Without elements like carbon, oxygen, and iron, there would be no rocky planets, no water, and no living things. Every planet, every living cell, is made from atoms forged in ancient stars. By tracing these elements, astronomers are learning how the ingredients for life are spread across the universe. Andromeda's stars, planets, and even its dust are all part of this grand cycle. By studying the light from Andromeda, scientists unlock the secrets of how the universe builds complexity from simple beginnings. The next time you look up at the night sky, remember, the atoms in your body were once part of a star, and galaxies like Andromeda are still shaping the story of life. Ghostly halos and invisible matter surround the Andromeda Galaxy, creating a mysterious and beautiful scene. When we look at Andromeda, we see its bright spiral arms and glowing core, but this is only a small part of the story. Beyond the visible stars lies a vast faint halo, a huge sphere of stars, gas, and something even stranger, dark matter. Astronomers first suspected something was missing when they measured how fast stars move in the outer parts of galaxies like Andromeda. The stars were moving much faster than expected, as if an invisible force was holding them together. This invisible force is what we call dark matter. It does not shine or block light, but its gravity shapes the galaxy. To understand this, scientists use computer simulations. They model galaxies with and without dark matter. Without dark matter, the outer stars would fly away into space. But with a dark matter halo, the galaxy holds together, and the stars move as we observe. These simulations help us see the invisible structure that surrounds Andromeda. The halo of Andromeda is not empty. It contains streams and shells of stars, remnants of smaller galaxies that Andromeda has torn apart and absorbed over billions of years. These tidal streams weave around the main disk like ghosts, telling a story of past collisions and cosmic cannibalism. One of the most famous is the giant stellar stream, a ribbon of stars stretching over 100,000 light-years. It likely formed when a dwarf galaxy was shredded by Andromeda's gravity. By mapping these streams, astronomers can trace the galaxy's violent history and learn how it grew over time. But what exactly is dark matter? Scientists know it is not made of ordinary atoms like the ones in stars, planets, or people. It does not emit, absorb, or reflect light. Its presence is revealed only by its gravity. Some theories suggest it could be made of unknown particles, while others propose new laws of physics. The true nature of dark matter remains one of the biggest mysteries in science. To study Andromeda's halo and its dark matter, astronomers use many tools. They observe how stars and gas move, measure the bending of light from distant objects, and look for faint streams of stars. They also use powerful telescopes and computer models to map the invisible mass. Each new discovery brings us closer to understanding the hidden structure of the universe. Even with all these efforts, many questions remain. What is dark matter made of? How did it shape the formation of galaxies like Andromeda? Will we ever be able to detect it directly? The answers to these questions could change our understanding of the universe forever. For now, Andromeda's ghostly halo and its invisible matter remind us that the universe is full of secrets waiting to be discovered. By studying these hidden structures, astronomers hope to unlock the story of how galaxies form, grow, and evolve across cosmic time. Dark matter and the cosmic web. When we look at Andromeda and other galaxies, we see beautiful spirals of stars, gas, and dust. But there is something invisible holding these galaxies together, something we call dark matter. Without it, the outer parts of galaxies would spin so fast that they would fly apart. Dark matter acts like a hidden glue, providing the extra gravity needed to keep everything in place. Scientists believe that about 85% of all matter in the universe is dark matter, even though we cannot see it or touch it. But what is dark matter? It is a mysterious form of matter that does not give off light or energy. We cannot see it directly, but we know it is there because of the way it affects things we can see. For example, when astronomers measure how fast stars move in the outer parts of Andromeda, they find that the stars are moving much faster than expected. The only way to explain this is if there is a huge amount of invisible mass, dark matter, surrounding the galaxy in a giant halo. Dark matter does not just surround individual galaxies, it also forms enormous structures that stretch across the universe. This is called the cosmic web. Imagine a giant, three-dimensional spider web made of invisible threads. These threads are made of dark matter, and galaxies like Andromeda are like tiny beads strung along them. Where the threads cross, we find clusters of galaxies, huge groups containing hundreds or thousands of galaxies bound together by gravity. The cosmic web is the backbone of the universe. It shapes where galaxies form, how they grow, and how they move. Most of the ordinary matter, like stars, planets, and gas, collects along these dark matter filaments. Over billions of years, gravity pulls gas and galaxies together along the web, creating the large-scale structure we see today. The local group, which includes Andromeda, the Milky Way, and many smaller galaxies, sits on one of these filaments, connecting us to even larger clusters like the Virgo cluster. How do astronomers study something they cannot see? They use clever techniques. By measuring how fast stars and gas move in galaxies, they can map out where dark matter must be. They also look at how light from distant galaxies bends as it passes through space, a phenomenon called gravitational lensing. This bending of light reveals the presence of massive amounts of dark matter, even when there is no visible matter there. Powerful computer simulations help scientists visualize how dark matter and the cosmic web evolve over time. Despite decades of research, the true nature of dark matter remains one of the biggest mysteries in science. Some experiments on Earth try to detect dark matter particles deep underground or in particle colliders. Others search the sky for faint signals from dark matter interactions. By mapping the dark matter halos of galaxies like Andromeda with ever greater detail, astronomers hope to solve this cosmic puzzle. Understanding dark matter and the cosmic web is key to unlocking the story of how galaxies form, how the universe grows, and ultimately, how we came to be. As we pause to take in the Andromeda Galaxy, let your eyes wander along its graceful spiral arms. Each swirl of stars and dust tells a story written over billions of years. The galaxy's glowing core shines at the heart of a vast shimmering halo, surrounded by lanes of cosmic dust that weave through the darkness. Music helps us feel the wonder of space. In documentaries, gentle melodies and soaring harmonies guide our emotions, making distant galaxies feel close and alive. As the music flows, it invites us to imagine drifting among the stars, exploring the mysteries that lie beyond our world. As you watch these scenes, let the music and images carry you through the vastness of space. The Andromeda Galaxy reminds us how much there is to discover and how beauty and mystery are always within reach, if we take a moment to listen and look. A family of companions. Andromeda is not alone in the universe. Surrounding this giant spiral galaxy are dozens of much smaller galaxies called dwarf galaxies. These dwarfs are tiny compared to Andromeda, with far fewer stars and much less mass. Yet they are important members of Andromeda's galactic family. Astronomers have found at least 30 dwarf galaxies orbiting Andromeda, and new ones are still being discovered. These companions include both bright and faint galaxies, some so dim that they are hard to spot even with powerful telescopes. Dwarf galaxies come in different shapes. Some are round and smooth, while others are irregular and full of young stars. Two of the most famous companions are M32 and M110. These are elliptical dwarf galaxies, which means they look like small, fuzzy balls of stars. Scientists think they may be the leftover cores of larger galaxies that collided with Andromeda long ago. Other companions, like NGC 147 and NGC 185, are irregular in shape and still making new stars today. These dwarf galaxies orbit Andromeda in complex paths. Some move in narrow planes or streams, almost like a cosmic dance. Over billions of years, gravity has pulled and twisted their orbits, sometimes causing them to pass close to Andromeda or even collide with it. When this happens, the smaller galaxy can be torn apart, its stars and gas added to Andromeda's outer regions. By studying these companions, astronomers learn how galaxies grow and change. The orbits and shapes of the dwarf galaxies reveal clues about Andromeda's history, how it has merged with other galaxies, and how its family has changed over time. Some dwarfs show signs of past collisions, while others are still mostly untouched. The local group, our cosmic neighborhood, is made up of Andromeda, the Milky Way, the Triangulum Galaxy, and dozens of dwarf galaxies. Andromeda's companions help scientists understand how galaxies interact and evolve together. Each dwarf galaxy is a piece of the puzzle, showing us how the universe builds large galaxies from many smaller ones. In the future, some of these companions may merge with Andromeda, adding their stars to its vast spiral. Others will continue to orbit for billions of years. Together, they remind us that even the largest galaxies are shaped by their smaller neighbors, and that the story of Andromeda is really the story of a whole family of galaxies moving through space together. Satellites and the local group. Astronomers are still discovering new satellite galaxies around Andromeda and the Milky Way. Some are so faint that they were only found in the last decade using deep sky surveys and advanced image processing. These discoveries help scientists understand how galaxies grow and interact over billions of years. By mapping the positions and motions of these satellites, researchers can trace the history of galaxy mergers, the influence of dark matter, and the structure of the cosmic web. Studying the local group gives us a window into the universe's past and helps us see how our own galaxy fits into the bigger picture of cosmic evolution. To wrap up our journey through Andromeda, let the awe and wonder of this majestic galaxy sink in. From the little cloud seen by ancient stargazers to the rich, swirling spiral revealed by modern telescopes, Andromeda shows us how far curiosity can take us. Its stars, dark matter and cosmic history connect us to the very origins of the universe and hint at the future of our own Milky Way. We'd love to hear from you. Tell us in the comments where you're watching from and what part of this journey fascinated you the most. Your insights help build a global community of space lovers, so share your thoughts and experiences below. If you enjoyed this exploration, please like the video and subscribe to our channel. We're dedicated to bringing you more exciting content on physics, astrophysics, cosmology, black holes, dark matter, exoplanets, quantum mechanics, gravitational waves, and cutting-edge space documentaries. Join us for regular dives into the mysteries of the cosmos. Your support keeps these journeys going, and we can't wait to explore the next cosmic frontier together. As we journey through Andromeda's mysteries, we are reminded of our place in an ever-expanding universe, one filled with wonder, ancient relics, and cosmic connections stretching across time and space. Every new discovery, hidden satellite galaxies, secrets of stellar birth and death, brings us closer to understanding not just Andromeda, but the story of all galaxies, including our own. Pause for a moment, look up at the night sky and remember, the light from Andromeda travels over 2 million years to reach us, a silent message from the distant past. Our curiosity, questions, explorations, are part of a much larger adventure, one that unites us as seekers of knowledge, gazing outward together. If this journey sparked your imagination, let us know your thoughts in the comments below. What fascinates you most about Andromeda? Don't forget to like and subscribe to join us for more cosmic stories. Together, we'll keep exploring the universe, one mystery at a time. Share your thoughts below, like and subscribe for more cosmic journeys.